Hello everyone, I welcome you all to this class. This is linear algebra class, and today we have this important topic to consider: similarity of matrices. Let's look at the definition we have on the board here. Let A and B be two square matrices, which means let A and B be n by n matrices. A and B are said to be similar if there exists an invertible square matrix P such that the inverse of that square matrix P multiplied by your matrix A multiplied by P will give you your matrix B. Then when this happens, we say that what? These two matrices A and B are said to be similar. Now you may be told to prove this theorem. We are going to state here that that similarity of matrices is an equivalent relation. So we are going to prove this theorem because you may be told to prove this theorem that similarity of matrices is an equivalent relation. So how do we prove this theorem? So let's start the proof of the theorem. Prove. Now, to prove that similarity of matrices is an equivalent relation, we must show that similarity of matrices satisfies the properties of an equivalent relation. Let's write something first. So let A, B, and C be square matrices. So we are going to show that similarity of matrices satisfies the following properties of equivalent relation. So for us to prove that similarity of matrices is an equivalent relation, we must show that it satisfies the properties of equivalent relation. So let's list those properties of equivalent relation, and each of them will show that similarity of matrices satisfies those properties. So the first property, which is reflexivity, is that every square matrix is similar to itself. We need to prove that this property holds, that every square matrix is similar to itself. So let's do that. Now A is equal to I inverse AI, where I is the identity matrix, right? I is identity matrix. So for any square matrix A, your A will be equal to the identity matrix, the inverse of identity matrix multiplied by A multiplied by what? Identity matrix. So every square matrix is similar to itself because there exists what? An invertible square matrix P. What is that invertible square matrix P? The identity matrix. Such that the inverse of that identity matrix multiplied by A multiplied by the identity matrix will give you the same thing as well, what? Matrix A. Thus, reflexivity holds. So it holds, right? So let's look at the second property. The second property is talking about symmetry. Symmetry property, which you can also say the symmetric property. So in the symmetry, we say that if your matrix A is similar to B, then B is similar to what? A. So if A is similar to B, then B will be similar to what? A. That's what we want to show. So let's show that this property holds. Let's show that this property holds. Now, let's suppose what they said first. If A is similar to B. So suppose that A is similar to B. Now this simply means that what? There exists an invertible square matrix P such that the inverse of P multiplied by matrix A multiplied by P will give you your matrix what? B. Right? Now, this equation is the same thing as saying, now this implies this implies that your matrix A, if you solve this equation, if you make your matrix A the solution of the formula, you are going to get what? Then your matrix A will be equal to P, B, P inverse. Right? If you are confused how we made A the solution of the formula, if you have this equation, the equation we have here is that B is equals to P inverse AP. This is the equation we have, right? Now, if you multiply this equation at the left by P and multiply it at the front by P inverse. So this side, multiply each side at the left by P, at the right by P inverse, at the left by P, at the right by P inverse. What are you going to get? You are going to have, so at the left by P, you are going to have P, B, you are going to have P, B, P inverse. So I multiply at the left by P, at the right by P inverse, right? Do the same thing this side, at the left by P, at the right by P inverse, right? So with this, you make your matrix A the solution of the formula, right? Because P inverse will give you the identity matrix, right? So you'll be doing identity matrix multiply with your matrix A, which is still your matrix A, multiply with identity matrix, right? So this simply will give you that your matrix A will be equal to P inverse, as we have it there, right? So I hope it's clear. So let's proceed. Now, remember what we have here. We're supposed to have the inverse of the invertible square matrix multiplied by your matrix multiplied by that invertible square matrix. Now, this simply implies that your matrix A will be equal to P inverse all inverse B P inverse, right? You know, P inverse will give you the same thing as P, right? So this, for us to proceed, we are going to call P inverse because the inverse of P will give another matrix, right? Let Q be equal to P inverse. This simply implies that your matrix A will be equal to, if you replace P inverse by Q, you have Q inverse, right? Then multiply by your matrix B, multiply by what? Q. So what do you notice? What we notice here is that what? B is similar to what? A. Because we suppose that A is similar to B, and we had that there exists an invertible square matrix P such that your B will be equal to P inverse AP, right? Now we solved and we got that B is similar to what? A, because there exists an invertible square matrix Q such that Q inverse B multiplied by Q will give you your matrix A. Hence B, right? B is similar to A. So the symmetric property holds. So the third property is transitivity. So we are going to prove that third property, transitivity. What's transitivity say? What does it say? If A is similar to B and B is similar to C, then A is similar to what? C. That's what the property says. Now what I wrote down here is, now A is similar to B because they say if A is similar to B, let's suppose that A is similar to B. Now, A is similar to B implies that there exists an invertible square matrix, let's call it P sub 1, such that the inverse of P sub 1 multiplied by A multiplied by P will give you your matrix B, right? And what I wrote here, the first one I wrote is that A is similar to B implies that there exists an invertible square matrix P such that the inverse of, we call it P sub 1, such that the inverse of P sub 1 multiplied by A multiplied by P will give you a matrix what? B. Now, they said, remember what transitivity says, that if A is similar to B, we have written that one down, right? And B is similar to C. That's why I say similarly, there exists an invertible square matrix P sub 2 such that this C will be equal to the inverse of P sub 2 multiplied by B multiplied by P sub 2, because we are assuming that what? B is similar to what? C. Then what we should prove is that if this happens, then A will be similar to what? C. This is what we want to show. So let's proceed here. Let's proceed here. Or we still have a little space here. This simply implies that your C will be equal to, so if you solve this equation, that your C will be equal to P sub 2 inverse. What is your B? See your B here, right? In this expression, B is P sub 1 inverse multiplied by A multiplied by P. So I'm going to replace it here. So instead of writing B, I'll write this. So I'm going to write P sub 1 inverse, right? I write P sub 1 inverse multiplied by A multiplied by P. That's your B, right? P sub 1. This is supposed to be P sub 1, right? P sub 1. Then multiply by what? P sub 2. So I hope this is clear. I replace your matrix B by this, right? Because B is P sub 1 inverse multiplied by A multiplied by P sub 1. So I replace it. So if we call P sub 1 P sub 2 something, because P sub 1 is an invertible square matrix, P sub 2 is an invertible square matrix, right? Their product is supposed to give you an invertible square matrix. So we are going to say let Q sub 2 be equal to, let me call this product Q sub 2 be equal to P sub 1 multiplied by P sub 2, right? So then we have when we are going to write this, let's write this C first. I'm going to have C will be equal to P sub 1 P sub 2 all inverse A P sub 1 P sub 2. This expression I wrote here, P sub 2 inverse multiplied by P sub 1 inverse, is same thing as, you write the second one first, it's same thing as P sub 1 multiplied by P sub 2 all inverse. So this is same thing as this. Then multiply, we have multiplied by matrix A multiplied by P sub 1 P sub 2, right? So remember, I've called P sub 1 P sub 2 Q sub 2. So this simply implies that your matrix C will be equal to, let's replace this P sub 1 P sub 2 by Q sub 2. So I'm going to have Q sub 2 inverse multiplied by A multiplied by what? Q sub what? 2. This simply means what? This simply means that A is similar to what? C. Hence A is similar to C, right? So A is similar to C. Why is it similar to C? Because we were able to find an invertible square matrix Q sub 2 such that the inverse of Q sub 2 multiplied by A multiplied by Q sub 2 will give you your matrix what? C. So this shows that what A is similar to C. Right? So let's conclude. So the conclusion here is therefore similarity of matrices is an equivalent relation. So that's what I've written down. Because the properties of equivalent relation has been satisfied, then similarity of matrices is an equivalent relation. So thank you so much for being part of this class. See you in the next class.